When you look up at the constellation Andromeda on a clear, dark night, your eyes might catch a faint, smudgy oval of light. It appears delicate, almost insignificant against the backdrop of the celestial sphere. But this modest smudge is an illusion born of vast distance. You are staring at the Andromeda Galaxy, the most massive structural heavyweight in our local group, holding over 1 trillion stars bound together in a perpetual gravitational dance. If human eyes were sensitive enough to detect the faint, extended glow of its outer structures, Andromeda would not appear as a tiny patch of cosmic fog. It would dominate the night sky, spanning a region 6 times wider than the diameter of the full moon. To truly comprehend this galactic behemoth, we must look far beyond what is visible to the naked eye and measure its true physical boundaries across the entire electromagnetic spectrum. Today, we are going to explore how big the Andromeda Galaxy really is. If you find this scientific journey insightful, feel free to like this video and subscribe to the channel. Also, please leave a comment below sharing where in the world you are currently watching from and what time it is for you right now. When astrophysicists measure Andromeda, they are not merely charting a static island of stars. They are calculating a sprawling, dynamic complex composed of stellar streams, massive star clusters, invisible dark matter, and an astonishingly vast gaseous envelope that reaches deep into intergalactic space. Standard astronomical figures traditionally quote a visible stellar disk diameter of roughly 220,000 light-years, making it nearly twice the width of our own Milky Way. Yet, cutting-edge space telescopes and multi-wavelength observations demonstrate that this luminous disk is only the dense nucleus of an extraordinarily larger cosmic architecture. The true dimensions of Andromeda fundamentally challenge how we define where a galaxy ends and where the void of deep space begins. The fundamental difficulty in grasping the size of the Andromeda Galaxy begins with the limitations of human visual biology. The human retina is a remarkable organ, but it evolved to detect bright, concentrated sources of light under an atmospheric filter, not faint, diffuse photons that have travelled across millions of light-years. When you step outside on a pristine night away from urban light pollution and direct your gaze toward the constellation Andromeda, your eyes are able to resolve only the dense, hyperluminous central core of the galaxy. This region, known to astronomers as the galactic bulge, contains an immense concentration of older, highly luminous stars packed closely together around a supermassive black hole. Because these stars are so densely concentrated, their combined light exceeds the threshold required to register on the rod cells of the human eye. However, the sprawling spiral arms and the vast, thin disk extending outward from this core contain stars that are spread far more thinly. The light from these outer regions arrives at Earth as a whisper, scattered over a wide area of the sky, falling well below the intensity needed to trigger human night vision. As a result of this biological limit, the visual impression of Andromeda is profoundly misleading. To the naked eye, the galaxy subtends an angular diameter of only about 1 degree, or roughly twice the width of the full moon. But if human eyes possessed the light-gathering power of a large telescope and could process photons across long integration times, the apparent size of Andromeda would expand dramatically. The full visible stellar disk spans an angular extent of approximately 3.16 degrees along its major axis. To put that into perspective, the full moon occupies roughly half a degree of sky. Therefore, if the outer spiral arms were fully visible to the naked eye, Andromeda would appear 6 times wider than the full moon, stretching across a portion of the night sky roughly equivalent to the width of 3 fingers held at arm's length. It would not look like an isolated, distant smudge, but rather a colossal, luminous wheel looming over the horizon, dominating the nighttime landscape in a manner that would completely transform our cultural and physical perception of the cosmos. Translating this angular size into physical dimensions requires a precise knowledge of distance, a measurement that proved to be one of the greatest challenges in the history of astronomy. Because an object can appear small either because it is genuinely tiny or because it is extremely far away, astronomers spent centuries debating whether Andromeda was a small cloud of gas sitting within our own Milky Way, or a vast, independent system located at an unimaginable distance. The true scale of Andromeda could only be calculated once humanity understood the mathematical relationship between angular diameter, physical radius, and distance. Using basic trigonometry, the physical diameter of an object is equal to twice its distance multiplied by the tangent of half its angular size. Once the distance to Andromeda was accurately measured at approximately 2.537 million light-years, or about 778 kiloparsecs, that modest angular span of 3.16 degrees transformed into a staggering physical diameter of over 220,000 light-years across its primary visible disk. The journey toward understanding this immense physical reality began over a millennium ago. The earliest recorded observation of the Andromeda Galaxy dates back to the 10th century, when the Persian astronomer Abd al-Rahman al-Sufi documented it in his landmark astronomical text, the Book of Fixed Stars. Al-Sufi described the object as a little cloud or a smudgy spot located near the constellation of the Andromeda. He noted its stationary nature relative to the surrounding stars, distinguishing it from transient phenomena like comets. For centuries, this object remained classified simply as a nebula, a term derived from the Latin word for cloud, used indiscriminately by early observers to describe any fuzzy, non-point-like astronomical source. When Galileo Galilei directed the first optical telescope toward the heavens in 1609, he revolutionized observational astronomy, but the true nature of Andromeda remained elusive. In 1612, the German astronomer Simon Marius provided the first telescopic description of Andromeda, famously comparing its soft, pale glow to the flame of a candle seen through a horn lantern. As optical technology advanced over the following 2 centuries, astronomers began to map the nebula with increasing precision. Charles Messier included it as the 31st object in his famous catalogue published in 1771, giving it the designation Messier 31, or M31, by which it is still widely known today. William Herschel, the pioneering British astronomer who discovered Uranus, observed M31 extensively in the late 18th century. Herschel believed he could detect a faint reddish hue near the centre, and mistakenly calculated that the nebula was relatively close to Earth, predicting its distance to be no more than 2,000 times the distance to the star Sirius. By the mid-19th century, a technological breakthrough altered the trajectory of galactic studies. In 1845, William Parsons, the 3rd Earl of Rosse, constructed a massive reflector telescope with a 6-foot aperture in Ireland, known as the Leviathan of Parsonstown. Lord Rosse used this instrument to resolve for the first time the distinct spiral structure of several prominent nebulae, most notably Messier 51. Although M31's inclined orientation made its spiral arms harder to disentangle, observers began to suspect that these spiral nebulae were not simple clouds of gas, but rather organized, rotating structures. The introduction of astronomical photography and spectroscopy in the late 19th century brought empirical rigor to the debate. In 1888, the Welsh astronomer Isaac Roberts captured the first long-exposure photograph of Andromeda, revealing clear concentric dust lanes and a distinct spiral architecture surrounding the bright nucleus. This visual evidence showed that M31 was an intricate, highly structured system, but it could not resolve the fundamental question of its scale. Was it a newborn solar system forming within the Milky Way? Or was it a vast star system located far beyond our galaxy's borders? In 1899, the German astronomer Julius Scheiner took the spectrum of light originating from Andromeda. His results provided a critical clue. The spectrum of M31 did not match the emission line spectra of glowing interstellar gas clouds like the Orion Nebula. Instead, it closely resembled the continuous absorption line spectrum of stars like our Sun. Scheiner correctly concluded that Andromeda was composed of billions of individual stars. But because telescopes of that era could not resolve these individual stars, the scientific community remained divided. This intellectual divide culminated in April 1920 during the famous Great Debate held at the Smithsonian Museum of Natural History in Washington, D.C., between 2 leading astronomers of the era, Harlow Shapley and Heber Curtis. Shapley argued for a single, massive Milky Way model. He believed that our galaxy was enormous, spanning over 300,000 light-years in diameter, and that all nebulae, including M31, were small, auxiliary objects contained within or located just outside the borders of the Milky Way. Curtis, on the other hand, championed the island universe hypothesis, an idea originally proposed in the 18th century by philosophers like Immanuel Kant. Curtis argued that the Milky Way was smaller, perhaps 30,000 light-years across, and that spiral nebulae were independent, comparable galaxies situated at immense intergalactic distances. Curtis pointed to observations of novae, exploding stars, within Andromeda. These novae appeared consistently several magnitudes fainter than novae observed in other parts of the night sky, suggesting that M31 was located millions of light-years away. The definitive resolution to the Great Debate arrived just 3 years later, in October 1923, through the work of Edwin Hubble, using the historic 100-inch Hooker telescope at Mount Wilson Observatory in California. Hubble was systematically photographing the spiral arms of Andromeda when he identified a variable star on a glass photographic plate. Initially marking it with an N for nova, he realized upon further analysis that the light output of this star rose and fell in a predictable rhythmic cycle. He crossed out the N and wrote VAR in bold red ink. Hubble had discovered a Cepheid variable star within Andromeda, a specific class of pulsating star whose intrinsic luminosity is directly proportional to its period of pulsation, a relationship discovered in 1912 by Henrietta Swan Leavitt. By measuring the period of the star, now known as Hubble Variable 1, or V1, Hubble calculated its absolute intrinsic brightness. Comparing this intrinsic brightness to its observed faintness allowed Hubble to compute its distance with unprecedented accuracy. Hubble initially calculated that Andromeda was located roughly 900,000 light-years away, a distance far beyond the boundaries of the Milky Way as understood at the time. This discovery shattered the traditional view of the universe, proving conclusively that Andromeda was an independent island universe, a sprawling system of stars equal to or greater than our own galaxy. Although later recalibrations of the Cepheid period luminosity relationship by Walter Baade in the 1950s and modern space-based measurements refined this distance to 2.537 million light-years, Hubble's 1923 discovery permanently redefined human knowledge of cosmic geography. By proving that Andromeda was a distinct, distant galaxy, astronomers unlocked the true scale of its physical size. What had appeared for centuries as a faint, unassuming smudge in the night sky was finally recognized as a massive cosmic structure spanning over 220,000 light-years of bright stellar material, embarking on a grand evolutionary journey across the deep expanses of space. The classic figure given for the physical scale of the Andromeda Galaxy is a stellar disk spanning roughly 220,000 light-years in diameter, when contrasted with the Milky Way, whose bright stellar disk is traditionally estimated at approximately 100,000 to 120,000 light-years across. Andromeda presents a structural profile of immense physical presence. To appreciate what a 220,000 light-year disk represents, one must examine the physical velocity and spatial duration required for light itself to traverse it. Photons emitted by stars on the absolute eastern periphery of Andromeda's visible stellar disk must travel through the vacuum of space for 220,000 years just to reach the westernmost edge. This spatial expanse contains hundreds of billions of stars, arranged in a complex multi-layered disk architecture that stretches far beyond what early optical surveys managed to capture. However, viewing the stellar disk of Andromeda as a simple flat two-dimensional geometric plane is a major misconception in modern astrophysics. When viewed through high-resolution deep space imaging and velocity mapping, Andromeda's disk reveals a dramatic three-dimensional warping known as a galactic warp. The outer plane of Andromeda's disk does not extend in a perfectly straight line. Instead, as one travels outward from the dense central galactic bulge toward the delicate outer rim, the disk curves significantly upward on one side and bends downward on the opposite side, taking on a pronounced integral-shaped or S-shaped spatial curvature. This galactic warp is a direct physical consequence of gravitational dynamics and tidal interactions. As a galaxy moves through intergalactic space, its vast stellar and gaseous disk responds to external gravitational forces exerted by passing satellite galaxies and the invisible, massive dark matter halo surrounding it. Over billions of years, dwarf galaxies like Messier 32 and Messier 110 have plunged through or orbited extremely close to Andromeda's primary plane. These gravitational encounters impart powerful tidal torques on the outer regions of the disk, where the local gravitational binding force of Andromeda's central core is weakest. The outer gas clouds and stellar orbits are pulled out of alignment with the central plane, producing a persistent long-term warp that precession transforms into a grand, undulating wave across the outer rim. Analysing the structural composition of Andromeda's disk requires dividing it into two distinct stellar components, the thin disk and the thick disk. The thin disk is the primary site of ongoing star formation and active stellar evolution. Spanning a vertical height of only a few hundred light-years relative to its immense horizontal diameter of 220,000 light-years, the thin disk is exceptionally flat along its inner radii. It is populated predominantly by younger, metal-rich population 1 stars, interstellar gas clouds composed of hydrogen and helium, and heavy cosmic dust grains formed from past supernova explosions. This thin layer is where the grand spiral arms reside, containing bright blue supergiant stars, ionized hydrogen regions, and glowing open clusters. Surrounding this thin disk is the thick disk, a far more diffuse, puffed-up stellar population that extends thousands of light-years above and below the galactic plane. The thick disk consists primarily of older, metal-poor population 2 stars that were formed billions of years ago during the tumultuous early assembly phase of the galaxy, or were gravitationally heated and kicked out of the thin disk during ancient galactic collisions. The existence of this prominent thick disk demonstrates that Andromeda's dynamic history is defined by recurring structural disruptions that have continuously reshaped its vertical geometry over cosmic time. Carved into this sprawling disk is Andromeda's distinctive spiral structure, though observing its true pattern presents unique astronomical challenges. Because Earth is situated almost directly along the orbital plane of Andromeda, viewing the galaxy at a steep inclination angle of approximately 77 degrees, its spiral arms appear compressed and layered on top of one another from our line of sight. Photometric analysis and radio observations mapping neutral hydrogen gas show that Andromeda is a grand, unbarred, or weakly barred spiral galaxy, classified under the Hubble sequence as an S-A-S-B galaxy. Unlike galaxies viewed face-on, which reveal sweeping, grand design spiral arms, Andromeda displays a more intricate, flocculent, and segmented arm network. The primary spiral arms branch outward from the central bulge in a sweeping, logarithmic spiral, but they are intersected by complex substructures, filamentary dust lanes, and localized gravitational spurs. The density wave theory explains how these spiral arms are maintained. The arms are not rigid physical structures like the spokes of a bicycle wheel, which would wind up and destroy themselves over a few galactic rotations. Instead, they are mobile waves of higher gravitational density that move through the disk at speeds different from the individual stars and gas clouds. As interstellar gas clouds enter one of these high-density spiral waves, the gas is compressed, triggering gravitational collapse within the clouds. This compressive process initiates intense bursts of new star formation along the leading edge of the spiral arms. Young, massive O and B-type stars are born within these dense regions. Because these high-mass stars shine with intense ultraviolet brilliance and burn through their nuclear fuel in only a few million years, they die before they can travel far from the spiral arms where they were created. Consequently, the spiral arms are illuminated like glowing cosmic highways, tracing the locations where massive stars are born and die. Interspersed throughout this spiral framework are vast rings and belts of cosmic dust and cool gas, which reveal the underlying metabolism of the galaxy. When observed in optical wavelengths, dust appears as dark, opaque, silhouetted lanes that block the light coming from stars lying behind them. However, when viewed in infrared wavelengths by space observatories such as the Spitzer Space Telescope and the Herschel Space Observatory, these cold dust lanes glow intensely, re-radiating absorbed starlight as thermal infrared energy. Infrared mapping of Andromeda revealed an extraordinary structural feature, a colossal offset ring of dust and gas located at a radial distance of approximately 32,000 light-years from the galactic core. This feature, often called Andromeda's Ring of Fire, spans over 65,000 light-years in circumference and dominates the galaxy's star-forming engine. This ring contains immense concentrations of cold molecular gas, primarily molecular hydrogen and carbon monoxide, which serve as the raw building blocks for future stellar generations. The presence of this massive ring, along with a secondary, smaller dust ring situated closer to the nucleus, provides profound clues regarding Andromeda's violent structural past. Numerical simulations indicate that these concentric dust rings are not standard features of isolated spiral galaxies. Instead, they are density waves produced by a head-on, off-axis collision with a smaller satellite galaxy, most likely the compact dwarf galaxy Messier 32, that occurred roughly 200 million years ago. As the satellite galaxy plunged directly through the centre of Andromeda's disk, like a stone dropped into a quiet pond, it generated an expanding circular shockwave that pushed gas and dust outward into a massive, concentrated ring. Beyond the inner ring of fire, dust lanes trail outward across the entire 220,000 light-year span of the disk. These dust grains are tiny particles of silicon, carbon, polycyclic aromatic hydrocarbons and ice, synthesized within the atmospheres of red giant stars and dispersed into the interstellar medium through planetary nebulae and supernova detonations. The total mass of dust within Andromeda's disk is estimated to be millions of times the mass of our Sun, acting as an insulating blanket that regulates the temperature of interstellar gas clouds, allowing them to cool down to near absolute zero, a thermodynamic requirement for gravity to pull gas together into new stars. The radial density profile of the stellar disk shows that stellar density falls off exponentially with distance from the center. Near the inner edge of the disk, stars are spaced relatively close together, creating a brilliant backdrop of continuous starlight. As one travels outward toward 80,000, 90,000, and 100,000 light-years from the core, the space between stars expands exponentially. At these extreme distances, the disk becomes extremely thin, faint, and diffuse, composed primarily of ancient, low-mass dwarf stars whose light output is faint. Measuring the true physical boundary of this stellar disk requires ultra-deep photometric surveys capable of detecting individual stars at extreme faintness levels, such as those conducted by the Pan-Andromeda Archaeological Survey. These surveys have demonstrated that while the bright primary stellar disk drops off sharply around 110,000 light-years from the center, yielding the standard 220,000 light-year diameter, scattered stars, faint outer stellar filaments, and low-density tidal debris extend much further. The outer edges of the physical disk merge seamlessly into complex stellar structures that blur the line between the disk itself and the surrounding galactic halo. In these distant outer reaches, the rotational motion of stars around the core becomes less organized, affected by the non-spherical shape of the dark matter halo and past gravitational collisions. The physical disk of Andromeda is thus not a rigid, static circle with a definitive hard border, but a dynamic, undulating 220,000 light-year structure characterized by warped edges, complex density waves, dense molecular rings, and a continuous exchange of energy that defines the life cycle of stars across hundreds of thousands of light-years. Beyond the visible perimeter of stars, dust, and glowing spiral arms lies the true spatial frontier of the Andromeda Galaxy, a colossal, invisible structure known as the gaseous halo. For decades, astronomers assumed that a galaxy's boundaries were defined by where its stars ceased to shine. However, modern astrophysics has revealed that the stellar disk, spanning 220,000 light-years across, is merely a dense island submerged within a vastly larger atmospheric reservoir of hot, ionized gas. This diffuse envelope, extending deep into intergalactic space, holds more mass than billions of stars combined, and plays a crucial role in regulating the galaxy's long-term evolution and growth. Because this gaseous halo consists of extremely low-density, highly ionized atoms, it emits almost no visible light, making it entirely invisible to traditional optical telescopes. To map this invisible sphere, scientists had to devise an ingenious observational strategy. This breakthrough arrived through the absorption map of ionized gas in Andromeda project, widely known as the OMEGA project. Led by astronomers utilizing the space-based capabilities of the Hubble Space Telescope, the OMEGA team transformed our understanding of galactic dimensions by using some of the most distant and energetic objects in the universe as background illumination sources. The methodology of the OMEGA project relied on cosmic coincidence and ultraviolet spectroscopy. Quasars, hyperluminous active galactic nuclei powered by supermassive black holes, located billions of light-years away, are scattered across the deep background of the cosmos. As the brilliant ultraviolet light from these distant quasars travels across the universe toward Earth, some of it passes directly through the invisible gaseous halo surrounding the much closer Andromeda Galaxy. Although the halo gas is far too diffuse to block starlight or emit detectable optical photons, specific ions within the halo absorb very precise, narrow wavelengths of the passing quasar light. By directing the cosmic origin spectrograph aboard the Hubble Space Telescope toward 43 distinct background quasars aligned behind and around Andromeda, the Amiga researchers measured the telltale absorption lines stamped onto the quasar light spectra. Specific, they analysed absorption signatures caused by highly ionized carbon, silicon, and oxygen atoms. The intensity and Doppler broadening of these absorption lines allowed astrophysicists to calculate the temperature, density, chemical composition, and physical distribution of the gas residing at various distances from Andromeda's central core. The results of the Amiga survey shocked the astronomical community, fundamentally redefining the physical size of the Andromeda Galaxy. The data revealed that Andromeda's gaseous halo extends outward from the galactic centre to a staggering radial distance of approximately 1.3 million to 2 million light-years in every direction. This means that the complete halo structure possesses a total physical diameter ranging from 2.6 million to 4 million light-years across. If human eyes could detect this ultraviolet-absorbing, ionized gas cloud in the night sky, Andromeda would not appear as a modest 3-degree smudge, or even a 20-degree stellar wheel. Its gaseous atmospheric footprint would span roughly 40 to 50 degrees across the firmament, occupying an area of sky thousands of times larger than the full moon. To fully grasp the immense physical scale of a halo, spanning up to 2 million light-years in radius, one must place it within the context of local cosmic geography. The physical distance separating the Milky Way galaxy from the Andromeda Galaxy is currently measured at approximately 2.537 million light-years. When you compare this spatial gap to the radial extent of Andromeda's halo, an extraordinary realization emerges. The outer frontier of Andromeda's gaseous halo is not isolated in deep space, but actually reaches more than halfway across the intergalactic expanse, dividing our two stellar systems. Even more remarkably, our own Milky Way possesses its own massive gaseous halo, extending hundreds of thousands of light-years into the surrounding vacuum. Because Andromeda's halo expands outward to a distance between 1.3 and 2 million light-years, the outer gaseous boundaries of the Milky Way and Andromeda are already touching, overlapping, and dynamically interacting with one another right now. The collision between our two galaxies has, in a very real thermodynamic sense, already begun at the gaseous level, billions of years before their primary stellar disks will collide and merge. Physical analysis of the halo gas reveals a complex multi-phase atmosphere held in place by Andromeda's deep gravitational potential well. The halo is not a uniform static fog, but a turbulent, structured ecosystem. The Amiga project identified a dual-layer architecture within this massive reservoir. The inner halo, extending out to roughly 100,000 to 300,000 light-years, is denser, warmer, and significantly enriched with heavy chemical elements, what astronomers refer to as metals. These heavy elements, including carbon, oxygen, neon, and silicon, were forged inside the core fires of massive stars within Andromeda's disk and subsequently blown out into the halo by violent collective supernova explosions and energetic stellar winds, a process known as galactic feedback. Beyond this inner zone lies the extended outer halo, stretching from 300,000 light-years out to the 2 million light-year boundary. This vast outer region consists of extremely rarefied high-temperature plasma, dominated by primordial hydrogen and helium gas, mixed with trace amounts of recycled stellar material. Despite its near-vacuum density, where an area the size of an entire planet might contain only a handful of gas atoms, the sheer volume encompassed by a sphere 4 million light-years in diameter translates into an immense total mass. Physicists estimate that the gas trapped within Andromeda's halo accounts for a significant fraction of the galaxy's total baryonic, or normal matter, providing a massive reservoir of cold and warm fuel that continuously rains back down onto the stellar disk over billions of years, sustaining new generations of star formation. The discovery of this 2 million light-year gaseous halo fundamentally alters how astrophysicists calculate the physical boundary conditions of massive spiral galaxies. It proves that what we observe through optical light, the bright, beautiful spiraling disk of stars, is merely the condensed heavy center of a far larger, invisible cosmic entity. The Omega project demonstrated that Andromeda is not an isolated island universe floating cleanly in a vast empty void, but an enormous atmospheric titan whose invisible gaseous arms reach out across millions of light years, actively embracing the surrounding intergalactic web and forging a direct physical link with our own home galaxy, long before the stars themselves ever meet. The discovery of Andromeda's 2 million light-year gaseous halo reveals that galaxies are not rigid, isolated structures, but dynamic fluid systems that constantly interact with their surrounding environment. As Andromeda moves through intergalactic space, its immense gravitational reach actively disrupts smaller dwarf galaxies and draws in pristine cosmic material. Embedded within its vast halo are the prominent physical signatures of past galactic cannibalism, monumental stellar streams that stretch across hundreds of thousands of light years, tracing the violent destruction of former satellite systems that strayed too close to Andromeda's gravitational center. The most magnificent of these structural remnants is the giant stellar stream, a massive, coherent filament of older stars that arcs across the southern quadrant of Andromeda's halo. Discovered through deep photometric mapping, this stellar stream extends outward from the galactic disk to a physical distance of over 125,000 light-years into the halo environment. The stream consists of hundreds of millions of ancient stars moving along aligned orbital trajectories, acting as a luminous trail of breadcrumbs left behind by a doomed dwarf galaxy. Supercomputer simulations reconstructing the gravitational mechanics of this stream indicate that roughly 2 billion years ago, a substantial satellite galaxy, with a mass equivalent to several billion suns, executed a close orbital passage through Andromeda's inner core. As this progenitor galaxy plunged through Andromeda's intense gravitational field, tremendous tidal forces tore it apart. The stronger gravitational gradient on the near side of the dwarf galaxy pulled its stars forward into an elongated tidal tail, while stars on the far side were flung backward into space. Over hundreds of millions of years, the dwarf galaxy was completely disrupted, its stellar population shredded and spread out along an immense orbital path that now wraps around Andromeda's outer halo. The giant stellar stream is far from the only remnant of galactic digestion surrounding Andromeda. High-sensitivity surveys, including the Pan-Andromeda Archaeological Survey, have uncovered a complex interconnected web of tidal features, including the Northern Arc, the Stream C and Stream D features, and vast diffuse stellar plumes that envelop the outer regions of the galaxy. Each of these structures represents the fossilized remains of a distinct dwarf galaxy, shredded by Andromeda over the past several billion years. The halo serves as a cosmic museum, preserving the dynamical history of these collisions, because orbital timescales at distances of 100,000 light-years or more are extraordinarily long, allowing these delicate stellar threads to remain visible for billions of years before thermalizing into the general halo field. While these stellar streams trace the history of solid stellar systems being consumed by Andromeda, a far more massive fluid interaction is taking place simultaneously within the gaseous halo itself. Because Andromeda's gaseous envelope extends up to 2 million light-years in radius, and the physical distance separating Andromeda from the Milky Way is approximately 2.537 million light-years, the outer boundaries of their respective gaseous halos are not separated by empty space. They are currently overlapping, compressing, and physically interacting in the intergalactic medium midway between the two galactic centers. This halo-halo interface represents the absolute leading edge of the impending collision between the Milky Way and Andromeda. Long before individual stars from either galaxy come anywhere near one another, the gaseous atmospheres surrounding both systems are experiencing high-velocity fluid dynamics and thermodynamic shocks. As Andromeda advances toward the Milky Way at roughly 110 km per second, the gas particles in the outer regions of both halos collide at supersonic relative velocities. These collisions convert the kinetic energy of the forward motion into thermal energy, heating the interacting gas layer to temperatures exceeding 1 million Kelvin. This shock-heated intergalactic gas emits faint, diffuse X-rays and ultraviolet radiation along the boundary region. The physical pressure generated at this interface, known as ram pressure, creates a compression wave that travels backward toward both galactic disks, altering the density profile of the surrounding intergalactic medium and triggering localized turbulence within the gaseous halos. Furthermore, this gaseous collision plays a critical role in stripping loose gas away from smaller dwarf galaxies caught in the crossfire. As satellite galaxies orbit between the Milky Way and Andromeda, they must pass through this high-density region where the two massive gaseous halos overlap. The combined ram pressure exerted by the overlapping gas strips the cold, star-forming hydrogen gas completely out of these dwarf galaxies, a process known as ram pressure stripping. This effectively quenches star formation within the satellite galaxies, transforming them into dormant dwarf spheroidals devoid of cold gas. The physical interaction between Andromeda's halo and the intergalactic environment also involves the continuous accretion of cold gas streams from the cosmic web. Running along intergalactic filaments, narrow ribbons of pristine, unshocked hydrogen gas slowly drain into Andromeda's gravitational potential well, feeding the halo with fresh material. As this incoming gas encounters the hot, shock-heated halo plasma, complex hydrodynamic instabilities, such as Kelvin-Helmholtz instabilities, cause the gas to mix, cool down, and condense into cold clouds. These condensed gas clouds eventually lose orbital angular momentum and rain down toward the central 220,000 light-year stellar disk. This continuous rain of cooling halo gas provides the essential raw fuel needed to sustain star formation within Andromeda's spiral arms over billions of years. Without this vast halo serving as an atmospheric buffer and gas reservoir, the galaxy would have exhausted its interstellar gas supply long ago, halting the birth of new stars. Thus, the region surrounding Andromeda is far from an empty vacuum. It is a highly dynamic, turbulent frontier, defined by shattered dwarf galaxies stretched into 100,000 light-year stellar streams, pristine filaments draining into the central core, and an active, high-velocity atmospheric collision with our own Milky Way that is fundamentally reshaping the intergalactic environment of the local group long before the stars themselves ever meet. Beyond its immense physical dimensions, the true scale of the Andromeda Galaxy is expressed through its staggering population of individual stars and massive stellar structures. While the Milky Way contains an estimated 100 billion to 400 billion stars, astrophysicists calculate that Andromeda holds roughly 1 trillion stars within its gravitational boundaries. This massive census, 1,000 billion individual stellar engines, makes Andromeda the dominant population centre of the local group. These stars are not evenly distributed throughout space. Instead, they are arranged in an exponentially increasing density gradient that transitions from the widely scattered, tenuous outer halo down to the hyperdense, blindingly luminous core. To understand what a population of 1 trillion stars implies for the physical architecture of Andromeda, one must analyse the density distribution across its various structural zones. In the outermost regions of the 220,000 light-year stellar disk, the interstellar distance between individual stars is vast. A traveller situated near the outer rim would see a night sky where neighbouring stars are separated by several light-years, much like the solar neighbourhood within the Milky Way, where our Sun sits roughly 4.2 light-years away from its nearest stellar neighbour, Proxima Centauri. However, as one moves inward toward the central bulge, the mean physical separation between stars shrinks dramatically. Within the central stellar bulge, a spherical, elevated hub of light spanning roughly 20,000 light-years in diameter, the spatial density of stars reaches extraordinary levels. In this central region, millions of ancient yellow and red dwarf stars, along with evolved red giants, are packed into volumes of space that would hold only a single star in the outer disk. Near the innermost light years surrounding the supermassive black hole, the average distance between stars decreases to a fraction of a light year, or mere light days apart. If an inhabited planet was situated near Andromeda's core, its nighttime sky would never know true darkness. Thousands of nearby stars would shine with the brilliant intensity of the full moon, illuminating the atmosphere in a continuous, multi-hued twilight created by the collective glow of millions of closely packed solar masses. This vast population of 1 trillion stars is divided into distinct stellar generations, known as Population 1 and Population 2 stars, which trace the chemical evolution of the galaxy over time. The younger, metal-rich Population 1 stars reside predominantly within the flat, gaseous spiral arms of the disk, where star formation continues to take place. These stars contain significant quantities of heavy chemical elements, such as carbon, oxygen, nitrogen, and iron, that were forged inside earlier generations of massive stars and ejected into space during catastrophic supernova explosions. Among these, Population 1 stars are immense, short-lived blue supergiants that radiate high-energy ultraviolet photons, heating the surrounding interstellar gas clouds and illuminating the sweeping spiral arm structures. In contrast, the central bulge, the thick disk, and the sprawling halo are populated primarily by Population 2 stars. These are extremely ancient stars, formed over 10 billion years ago during the early collapse of the protogalactic gas cloud. They are metal-poor, possessing atmospheres composed almost entirely of primordial hydrogen and helium, with only trace amounts of heavier elements. Because low-mass Population 2 stars burn through their core hydrogen fuel at an exceptionally slow rate, billions of these stellar embers have survived since the dawn of cosmic history, serving as living fossil records of Andromeda's initial formation phase. Gravitationally bound to this trillion-star system is an extraordinarily extensive network of globular clusters, tight spherical swarms containing hundreds of thousands to millions of stars, packed into a region only a few dozen to a few hundred light-years across. While the Milky Way harbours a modest halo system of approximately 150 to 160 globular clusters, deep sky surveys confirm that Andromeda possesses a colossal network of over 500 globular clusters distributed throughout its disk, bulge, and outer halo. This massive globular cluster system provides crucial insights into the formation history and gravitational reach of Andromeda. Because globular clusters are among the oldest bound stellar structures in the universe, their spatial distribution, metallicities, and orbital kinematics act as a dynamic roadmap of past galactic mergers. Many of the globular clusters orbiting in Andromeda's outer halo do not follow circular, orderly paths aligned with the central disk plane. Instead, they move along highly eccentric, inclined orbits, swinging through the halo at random angles. Spectroscopy reveals that these outer halo clusters fall into distinct subpopulations with varying chemical compositions, proving that a significant fraction of Andromeda's globular clusters were not born within M31 itself. Instead, they were stripped away from smaller dwarf satellite galaxies that were gravitationally torn apart and absorbed by Andromeda over billions of years of cosmic cannibalism. Standing at the absolute apex of this 500 cluster network is Male 2, also designated as Globular Cluster 1, or simply G1. Located at a projection distance of approximately 130,000 light-years from Andromeda's central core, G1 is the most massive and luminous globular cluster in the entire local group. Containing over 2 million stars and possessing a total mass equivalent to roughly 10 million times the mass of our Sun, G1 is more than twice as massive as Omega Centauri, the largest globular cluster orbiting the Milky Way. G1 is so massive and structurally complex that many astrophysicists argue it should not be classified as a standard globular cluster at all. High-resolution optical imaging by the Hubble Space Telescope and radial velocity mapping demonstrate that G1 exhibits a complex stellar population with multiple generations of star formation, a characteristic that standard globular clusters, which typically form in a single rapid burst, do not possess. Furthermore, kinematic measurements of star velocities near the centre of G1 suggest the presence of an intermediate mass black hole, weighing approximately 20,000 solar masses, embedded at its core. These physical characteristics strongly indicate that Male 2 is the surviving, hyperdense stellar core of an ancient dwarf galaxy, whose outer envelope of gas, dust, and stars was completely stripped away by Andromeda's immense tidal forces long ago. As Andromeda consumed the parent galaxy, the ultra-dense central core resisted complete tidal destruction, surviving as a distinct, massive cluster that continues to circle Andromeda in a high eccentricity orbit across the far reaches of the halo. The sheer numerical dominance of Andromeda's stellar census, 1 trillion stars organised into a dense central bulge, sweeping spiral arms, and an immense halo populated by over 500 globular clusters, presents a structural portrait of a true galactic giant. This vast stellar population continuously cycles matter through star formation, nuclear fusion, and supernova feedback, driving the thermodynamic evolution of an island universe that stands as the undisputed demographic titan of our local cosmic neighborhood. Estimating the absolute mass of a galaxy spanning over 220,000 light-years in visible diameter requires going beyond merely counting its stars, gas clouds, and dust lanes. In modern astrophysics, the luminous baryonic matter, everything that emits or absorbs light, represents only a minor fraction of a galaxy's total structural mass. To measure the true, total physical weight of the Andromeda Galaxy, astronomers must analyze its gravitational impact on the motion of objects orbiting at its extreme outer edges. This dynamic approach reveals that Andromeda is embedded within an immense, invisible reservoir of dark matter that extends far past its visible stellar disk, dictating the orbital mechanics of the entire system. The primary method used to weigh Andromeda relies on measuring its rotation curve, the plot of the orbital velocities of stars and interstellar gas clouds as a function of their radial distance from the galactic center. Under classical Newtonian mechanics and Keplerian motion, one would expect that once an observer moves past the dense central bulge where most of the luminous mass is concentrated, the orbital speeds of stars in the outer disk should drop off significantly, inversely proportional to the square root of their distance from the core. This is precisely how our solar system behaves, where distant planets like Neptune orbit the Sun at far slower speeds than inner rocky planets like Mercury. However, when spectroscopic observations of Andromeda were conducted, most famously pioneered by astronomer Vera Rubin and her colleagues in the late 1960s and 1970s, the data presented a profound contradiction to classical expectations. By measuring the Doppler shift of spectral emission lines, such as the 2.1 centimeter radio line of neutral atomic hydrogen gas extending across the outer disk, Rubin mapped the rotation velocities of Andromeda out to extreme radii. Instead of showing a sharp decline in speed at greater distances, Andromeda's rotation curve flattens out. The hydrogen gas and stars residing 60,000, 80,000, and 100,000 light-years from the center continue to orbit at a nearly constant, remarkably high speed of approximately 220 to 250 kilometers per second. If the galaxy contained only the mass visible in its stars, gas, and dust, the gravitational pull in these outer regions would be far too weak to keep these fast-moving stars in orbit. Without an enormous additional source of unseen mass, the outer regions of Andromeda's disk would fly apart into intergalactic space. To account for this flat rotation curve and keep the disk gravitationally bound, astrophysicists calculated that Andromeda must be enveloped by an enormous extended dark matter halo. Dark matter is a form of matter that does not interact with electromagnetic radiation, making it completely invisible to optical, radio, ultraviolet, and X-ray telescopes. Its presence is inferred purely through its gravitational effects on visible matter and the path of light travelling through space. Detailed gravitational modelling of Andromeda's rotation dynamics reveals the vast discrepancy between its luminous mass and its dark matter mass. The total mass of all the baryonic matter in Andromeda, including its 1 trillion stars, interstellar gas, cosmic dust, and compact stellar remnants, is estimated at roughly 100 billion to 150 billion times the mass of our Sun. While 100 billion solar masses is an extraordinarily large quantity of normal matter, it accounts for less than 10% of the galaxy's total gravitational weight. The remaining 90% or more of Andromeda's mass is locked away in its invisible dark matter halo. Calculations incorporating the orbital dynamics of distant satellite galaxies, planetary nebulae, and the velocities of globular clusters moving in the outer halo place the total mass of Andromeda, including dark matter, between 1.0 trillion and 1.5 trillion solar masses. In scientific notation, this equals over 2 times 10 to the power of 42 kilograms of matter bound together by gravity. The spatial distribution of this dark matter halo is fundamentally different from that of the stellar disk. While stars, dust, and gas have collapsed into a relatively thin, highly organized rotating disk and dense central bulge due to energy dissipation through radiation, dark matter particles do not readily lose energy through collisions or radiation. Consequently, The dark matter halo forms a vast, roughly spherical or triaxial envelope that surrounds the entire visible galaxy. This invisible halo extends far beyond the 220,000 light-year stellar disk, stretching outward to a physical radius of over 1 million light-years from the core. At these extreme distances, the density of dark matter drops off gradually, smoothly merging into the large-scale web of intergalactic space. The deep gravitational potential well created by this trillion solar mass dark matter envelope acts as the anchor for everything within Andromeda's influence. It holds the high-velocity outer stars in their orbits, binds the 500 globular clusters, traps the massive 2 million light-year gaseous atmosphere, and pulls surrounding dwarf satellite galaxies into long-term orbital trajectories. Comparing the mass of Andromeda to that of the Milky Way has historically been a topic of intense debate among astrophysicists. For decades, Andromeda was widely considered to be significantly more massive than the Milky Way in every metric, possessing both more stars and a larger dark matter halo. However, recent advances in precision astrometry, particularly data from space missions measuring three-dimensional stellar velocities, have refined these mass estimates. While Andromeda clearly holds roughly twice as many stars as the Milky Way and boasts a larger visible stellar disk, refined gravitational measurements suggest that the Milky Way's dark matter halo may be denser and more compact than previously thought. As a result, the total masses of the Milky Way and Andromeda are now understood to be surprisingly comparable, with both systems falling within the range of 1 trillion to 1.5 trillion solar masses. Nevertheless, the vast spatial extent of Andromeda's dark matter halo ensures its dominance over local cosmic space. By exerting a relentless gravitational pull across millions of light-years, this vast halo continuously draws surrounding matter toward its centre. It is this total physical mass, driven overwhelmingly by dark matter, that determines the trajectory of the entire local group, pulling Andromeda and the Milky Way toward one another and setting the stage for their grand cosmic merger billions of years in the future. At the absolute centre of the Andromeda Galaxy sits a dynamic gravitational anchor that governs the orbital architecture of its innermost regions, a supermassive black hole designated as M31 star. While the 220,000 light-year stellar disk and the trillion solar mass dark matter halo dominate the macrostructure of the galaxy, M31 star exerts total control over the central core. To understand the physical scale of this central monster, one must compare it directly to Sagittarius A star, the supermassive black hole residing at the centre of our own Milky Way. Sagittarius A star possesses a mass equivalent to approximately 4 million times the mass of our Sun, which is a formidable concentration of matter crammed into a region smaller than the orbit of Mercury. However, astrophysicists estimate that M31 star holds a staggering mass of roughly 100 million to 140 million solar masses, making it roughly 25 to 35 times more massive than the Milky Way's central black hole. The physical radius of a black hole is defined by its Schwarzschild radius, the boundary marking the event horizon beyond which the gravitational pull is so intense that not even light can escape. For a supermassive black hole weighing 100 million solar masses, the event horizon extends outward to a physical radius of approximately 300 million kilometers, or roughly 2 astronomical units. This means that if M31 star were placed at the position of our Sun, its event horizon would completely swallow the orbits of Mercury, Venus, Earth, and Mars, stretching out toward the inner main asteroid belt. The immense mass of M31 star generates an extremely steep gravitational potential gradient, causing stars in its immediate vicinity to orbit at extreme velocities, exceeding several thousand kilometers per second. Despite its immense mass, M31 star currently exists in a relatively quiet, quiescent operational state. Inactive galactic nuclei, or bright quasars found in the distant universe, supermassive black holes actively devour massive quantities of interstellar gas and dust. As this material falls inward toward the event horizon, it forms a rapidly spinning accretion disk, where kinetic energy is converted into radiation through magnetic friction and viscous dissipation, causing the core to illuminate the entire galaxy across X-ray, ultraviolet, and optical wavelengths. In contrast, M31 star is currently starved of a continuous, high-volume supply of cold gas. The rate at which it accretes matter is exceptionally low, radiating far below its theoretical maximum brightness, known as the Eddington limit. However, high-energy observations conducted by X-ray space observatories, such as the Chandra X-ray Observatory and the XMM Newton satellite, confirm that M31 star is far from dead. Chandra's sharp, sub-arc-second spatial resolution allowed astronomers to isolate the faint X-ray emission generated directly at the location of M31 star, distinguishing it from surrounding stellar X-ray sources like low-mass X-ray binaries and supernova remnants. The detected X-ray spectrum reveals low-level accretion activity, where small amounts of gas shed by surrounding red giant stars slowly drain into the central gravitational sink. Occasionally, M31 star undergoes minor flares across X-ray and radio wavelengths, signaling the destruction and consumption of small gas clumps or the erratic capture of passing stellar debris. The physical region immediately surrounding M31 star contains one of the most enigmatic structural features observed in extragalactic astronomy, the double nucleus phenomenon. When the Hubble Space Telescope directed its planetary camera toward the central core of Andromeda in the early 1990s, astronomers expected to see a single, symmetrical point of peak brightness marking the central stellar density peak. Instead, the high-resolution optical images revealed two distinct luminous peaks, separated by a spatial distance of only 0.49 arcseconds, which translates at Andromeda's distance to a physical separation of roughly 5 light-years. These two nuclear components were designated P1 and P2. The bright P1 peak is offset from the geometric center of the galaxy and shines with a distinct yellowish light dominated by cooler, older red giant stars. The dimmer P2 peak sits directly at the true dynamical center of the galaxy and coincides exactly with the precise position of the supermassive black hole M31 star. Spectroscopy of the P2 region reveals that it is surrounded by a dense cluster of hot, young, ultraviolet luminous blue stars, arranged in a compact disk measuring less than 1 light-year across. For years, the existence of a double nucleus presented a profound theoretical puzzle. Initial hypotheses suggested that astronomers were witnessing the immediate aftermath of a major galactic merger, where the dense stellar core of a consumed dwarf satellite galaxy was actively spiraling into Andromeda's central black hole. However, dynamic modelling and orbital simulations disproved this cannibalism scenario. A separate, unbound stellar core orbiting 5 light-years from a 100 million solar mass black hole would experience rapid orbital decay due to dynamical friction with surrounding stars, dissolving into a smooth, featureless stellar distribution in less than a few million years. The persistent stability of the double nucleus required a completely different physical explanation. The definitive solution to the double nucleus mystery was formulated by astrophysicist Scott Tremaine through the eccentric disk model. Tremaine demonstrated that P1 and P2 are not two separate physical clusters of stars colliding in space. Instead, they represent two different structural regions of a single, highly eccentric ring-like disk composed of millions of older stars orbiting M31 star along aligned elliptical trajectories. This eccentric disk spans a physical radius of roughly 5 to 10 light-years, surrounding the supermassive black hole. To understand why an eccentric disk creates the optical illusion of two distinct nuclei, one must apply Kepler's second law of planetary motion, which dictates that an object moving along an elliptical orbit travels slowest when it is near apocenter, the furthest point from the gravitational focus, and fastest when it is near pericenter, the closest point to the focus. Because millions of stars within this eccentric disk share aligned elliptical paths, stars naturally accumulate near their apocenter positions, where they spend the majority of their orbital period moving at reduced speeds. This physical traffic jam of stars at the apocenter creates a high local density of starlight, producing the bright, offset peak known as P1. Conversely, the dimmer P2 peak represents the location of the central gravitational focal point itself, where the supermassive black hole M31 star resides. At pericenter, stars sweep rapidly around the black hole at extreme velocities. While the density of stars at pericenter is high due to the narrow spatial convergence of orbital paths, the stars pass through this region so quickly that they do not pile up in the same way they do at apocenter. However, The presence of the separate disk of young, hot blue stars bound directly to M31 star at pericenter provides the optical emission that defines P2. This surrounding disk of young blue stars within P2 introduces an additional astrophysical puzzle. Because the tidal gravitational forces exerted by a 100 million solar mass black hole at distances of less than 1 light-year are extraordinarily intense, standard molecular gas clouds should be violently torn apart long before they can gravitationally collapse to form new stars. Yet the blue stars in the P2 disk are estimated to be less than 200 million years old. This indicates that despite the hostile tidal environment surrounding M31 star, high-density gas disks occasionally form close to the event horizon, likely triggered by the tidal disruption of passing gas clouds or collisions between giant molecular clouds, initiating intense, localized starburst events that give birth to massive stars right in the gravitational shadow of the central black hole. The dynamical relationship between M31 star, the eccentric stellar disk producing the P1 apocenter peak, and the blue star disk marking the P2 pericenter core demonstrates the complex equilibrium governing the centers of massive spiral galaxies. M31 star acts as the central engine around which the core dances, maintaining an intricate gravitational balance that spans light years, anchoring the 1 trillion stars of Andromeda around 100 million solar mass heart. The structural domain of the Andromeda Galaxy extends far beyond its primary disk, halo, and central black hole, encompassing an extensive network of satellite systems locked in its gravitational grip. Bound within Andromeda's massive dark matter potential well is a diverse family of dwarf galaxies, ranging from compact dwarf ellipticals to diffuse dwarf spheroidals. Just as planets orbit a central star, these smaller galaxies orbit Andromeda across millions of cubic light-years of space, acting as dynamic tracers of the galaxy's gravitational boundary and evolutionary history. Analyzing this satellite network provides a direct window into the gravitational mechanics, tidal interactions, and structural organization of the local group's largest galactic system. At the center of Andromeda's satellite population are its most prominent and luminous companion galaxies: Messier 32, Messier 110, NGC 147, and NGC 185. Messier 32, or M32, is an exceptionally rare compact dwarf elliptical galaxy situated at a projection distance of only 22,000 light-years from Andromeda's core, appearing superimposed against its outer spiral arms. Containing roughly 3 billion stars packed into a physical diameter of less than 8,000 light-years, M32 exhibits an abnormally high central stellar density and a supermassive black hole weighing approximately 10 to 20 million solar masses. The extreme structural properties of M32 are the direct result of violent tidal interactions with Andromeda. Astrophysical modelling demonstrates that M32 was originally a much larger, fully developed spiral galaxy that executed a close, penetrating passage through Andromeda's disk roughly 2 billion years ago. As M32 plunged toward Andromeda's central core, Andromeda's tremendous tidal forces executed severe galactic stripping. The fragile outer spiral arms, gas reservoirs, and dark matter halo of M32 were ripped away and absorbed into Andromeda's disk and halo, leaving behind only the hyperdense central stellar core and black hole that we observe today. M32 stands as a classic example of a tidal compact dwarf, stripped down to its innermost core by the gravitational fury of its parent host. In contrast, Messier 110, or M110, represents a dwarf elliptical galaxy situated further out at a projection distance of roughly 190,000 light-years. M110 is structurally larger and more diffuse than M32, spanning approximately 15,000 light-years in diameter. Unlike typical dwarf ellipticals, which are composed almost entirely of ancient, dormant stars, M110 contains unexpected clouds of interstellar gas and dust, along with populations of relatively young blue stars near its center. High-sensitivity orbital simulations indicate that M110 is currently undergoing its first or second close passage through Andromeda's outer halo. As M110 continues its orbital trajectory, the ram pressure exerted by Andromeda's hot, gaseous atmosphere will eventually strip away these remaining gas reserves, quenching its star formation permanently. Beyond these bright, historically catalogued companions lies a sprawling swarm of smaller, low-luminosity dwarf spheroidal galaxies, designated chronologically from Andromeda 1 through Andromeda 30. These dwarf systems possess extremely low surface brightnesses, containing anywhere from a few 100,000 to several million stars spread across thousands of light-years. Because their stellar densities are so low, these dwarf galaxies are composed predominantly of dark matter, with visible stars contributing only a fraction of a percent to their total mass. Their orbits take them through the deep gravitational potential well of Andromeda's trillion solar mass dark matter halo, where tidal forces continually distort their boundaries and pull off long, faint streams of stars. Mapping the three-dimensional spatial distribution and line-of-sight velocities of this satellite swarm led to one of the most profound and unexpected discoveries in modern extragalactic astronomy: the Great Plane of Andromeda. Standard cosmological theory, specifically the cold dark matter model, predicts that dwarf satellite galaxies should be pulled into a primary galaxy's halo along random, isotropic vectors from all directions in space. Over billions of years, these satellites should form a roughly spherical, isotropically distributed cloud, orbiting chaotically around the central system. However, precise astrometric surveys conducted by the Pan-Andromeda Archaeological Survey revealed that Andromeda's satellites do not follow a random, spherical distribution. Instead, a major fraction of Andromeda's satellite galaxies, at least 14 out of 27 surveyed dwarf systems, are confined to a remarkably thin, highly flattened geometric plane extending over 1.3 million light-years in radius across the halo. This flattened plane has a thickness of only roughly 45,000 light-years, making it extraordinarily thin relative to its immense horizontal span. Even more remarkably, velocity measurements obtained through spectroscopic Doppler shifts demonstrate that the satellite galaxies embedded within this plane are not moving randomly. Instead, they share a coherent, co-rotating orbital pattern. Over half of Andromeda's dwarf satellites are rotating in the same direction around Andromeda's central core within this razor-thin plane, forming a giant coherent wheel of dwarf galaxies sweeping through intergalactic space. The existence of this vast, thin, co-rotating satellite plane presents a major puzzle for standard cosmological models. Statistically, the probability of a random, isotropic distribution of dwarf galaxies spontaneously aligning into a coherent, co-rotating structure 45,000 light-years thin across a 2 million light-year halo is less than 0.1%. This discrepancy suggests that current dark matter simulations may be missing fundamental physics regarding how matter collapses and accretes on galactic scales, or that the formation history of Andromeda's satellite system was driven by an extraordinary, large-scale event. To explain the mystery of this planar alignment, astrophysicists have proposed two primary theoretical models: the cosmic Webb filament model and the tidal dwarf galaxy model. The cosmic Webb filament model suggests that the alignment is a natural consequence of large-scale structure formation. On cosmological scales, dark matter and gas are organized into immense cosmic filaments that cross the universe. Galaxies grow by accreting matter that flows along these narrow, high-density cosmic highways. If Andromeda is situated at the junction of a major cosmic filament connecting it to the broader universe, dwarf galaxies would naturally be channeled into Andromeda's halo along a narrow, two-dimensional direction, giving the appearance of a coherent, flattened plane. The alternative explanation is the tidal dwarf galaxy hypothesis, which attributes the satellite plane to an ancient major merger event. If Andromeda experienced a close collision or merger with another massive galaxy several billion years ago, such as the progenitor of M32, or an ancient companion, the intense gravitational torque would have flung vast tidal tails of gas and stars deep into intergalactic space along a single, flattened orbital plane. Over time, these extended tidal streams would gravitationally fragment and condense, giving birth to dozens of new, low-mass dwarf galaxies, sharing identical orbital inclinations and rotation directions. Resolving the origin of the Great Plane of Andromeda is complicated further by the realization that our own Milky Way possesses a strikingly similar feature known as the vast polar structure, a flattened plane of co-rotating dwarf satellite galaxies orbiting perpendicular to the Milky Way's galactic disk. The presence of thin, co-rotating satellite planes surrounding both of the local group's primary galactic systems indicates that co-rotating planar structures are not rare anomalies, but may be a fundamental property of massive spiral galaxies. Whether formed through filamentary accretion along cosmic web channels or generated during violent ancient tidal collisions, Andromeda's satellite network demonstrates the immense spatial reach of its gravitational influence. Spanning over 1.3 million light-years in radius, this network of dwarf ellipticals, tidally stripped cores, and co-rotating spheroidal galaxies continuously interacts with Andromeda's halo, mapping out the invisible dark matter structure and dynamic history of a galactic titan. To fully comprehend the absolute physical dimensions and metabolic interior of the Andromeda Galaxy, optical light alone is fundamentally insufficient. Visible starlight reveals only a narrow slice of the electromagnetic continuum, capturing primarily the thermal emission from mainstream stellar populations, while obscuring vast quantities of matter hidden behind interstellar dust or glowing at extreme energies. By observing Andromeda through multi-wavelength astronomy, spanning X-rays, ultraviolet radiation, infrared wavelengths, and radio waves, astronomers dismantle the visual illusions created by cosmic dust and reveal the complete physical inventory of gas, dust, high-energy particles, and stellar remnants that define this 220,000 light-year giant. At the highest energy end of the spectrum, X-ray astronomy opens a window into the most violent, and highly evolved environments within Andromeda. Observed by space observatories such as the Chandra X-ray Observatory and XMM Newton, Andromeda transforms from a serene spiral of starlight into a dramatic canvas illuminated by hundreds of point-like high-energy sources and diffuse, superheated plasma. High-resolution X-ray mapping has catalogued over 500 individual X-ray sources scattered across the stellar disk, central bulge, and inner halo. The vast majority of these point sources are low-mass X-ray binaries and high-mass X-ray binaries. These systems consist of a compact stellar remnant, either a stellar mass black hole or a hyperdense neutron star, orbiting in extremely close proximity to a normal companion star. As the companion star evolves, its outer gaseous layers are pulled across the Roche lobe into an accretion disk surrounding the compact remnant. As this gas spirals inward, gravitational potential energy is converted into kinetic friction, heating the inner accretion disk to temperatures exceeding 10 million Kelvin and emitting intense, flickering X-ray photons. Furthermore, X-ray surveys reveal numerous supernova remnants dotting the spiral arms, expanding bubble shocks where massive stars ended their lives in catastrophic explosions. These expanding blast waves heat the surrounding interstellar gas to millions of degrees, creating a hot, ionized, diffuse gas phase that fills the cavities between star-forming regions. By mapping the spatial distribution and energy spectra of these X-ray sources, astrophysicists can calculate the historical supernova rate across the disk, track the population of dead stellar cores, and measure how energetic feedback from exploding stars heats the interstellar medium and drives gas out into the halo. Moving down the energy spectrum to ultraviolet wavelengths, observatories like the Galaxy Evolution Explorer, or GALEX, capture the active, ongoing star formation engine of Andromeda. Photons in the far ultraviolet and near ultraviolet regimes are emitted almost exclusively by short-lived, high-mass O and B-type stars. These stellar giants possess surface temperatures ranging from 10,000 to over 50,000 Kelvin, radiating the overwhelming majority of their energy as ultraviolet light. Because these high-mass stars exhaust their nuclear fuel in only a few million to a few tens of millions of years, their presence in ultraviolet images acts as an unambiguous marker of recent star formation. Galax images of Andromeda present a striking contrast to optical views. While optical photographs are dominated by the bright, smooth, yellow-white glow of the central stellar bulge, composed of billions of ancient evolved stars, ultraviolet images show the central bulge as relatively dark and dormant. Instead, the ultraviolet light traces a brilliant, glowing skeleton of grand spiral arms and concentric rings. The most prominent feature in ultraviolet light is the colossal 32,000 light-year ring of fire, which glows with extraordinary intensity. This ring represents a continuous sweeping zone of active starburst activity, where cold gas is actively collapsing into thousands of open star clusters, populating the outer disk with massive blue supergiants. Ultraviolet mapping allows astronomers to measure the global star formation rate of Andromeda, currently estimated at roughly 1 solar mass per year, providing a direct metric of how rapidly the galaxy is consuming its remaining cold gas reserves. While ultraviolet radiation highlights hot, young stars, infrared astronomy penetrates deep into the dark, opaque dust lanes that hide these stellar nurseries from optical view. Space observatories such as the Spitzer Space Telescope and the Herschel Space Observatory operate in the mid-infrared and far-infrared regimes, revealing an entirely different physical landscape. Interstellar dust grains, composed of microscopic particles of carbon, silicates, and complex organic molecules known as polycyclic aromatic hydrocarbons, are exceptionally efficient at absorbing ultraviolet and optical light emitted by nearby stars. This absorbed light heats the dust grains to temperatures between 10 and 100 Kelvin above absolute zero. At these cold temperatures, dust re-radiates the absorbed energy as thermal far-infrared light. Infrared mapping conducted by Spitzer and Herschel transformed our understanding of Andromeda's gas-to-dust architecture. In infrared wavelengths, the dark, silhouetted dust lanes observed in optical photographs light up as luminous, intricate ribbons of thermal emission that weave through the entire 220,000 light-year disk. These infrared observations confirmed the existence of the secondary, inner dust ring, located near the central core, positioned at a radius of roughly 2,000 light-years from the supermassive black hole, in addition to the massive 32,000 light-year outer ring. The total mass of dust within Andromeda is calculated from far-infrared flux measurements to be several million times the mass of our Sun. Dust is far more than a cosmic optical nuisance. It acts as an essential coolant for the interstellar medium. By radiating away thermal energy, dust allows interstellar gas clouds to maintain the near-zero temperatures necessary for gravitational pressure to overcome thermal expansion, enabling gas to collapse and form future generations of stars. At the longest electromagnetic wavelengths, radio astronomy provides the ultimate tool for measuring the absolute spatial boundary, kinematic rotation, and neutral gas content of Andromeda. Using giant radio telescope networks and single-dish antennas, such as the Effelsberg 100-meter radio telescope and the Very Large Array, astronomers observe Andromeda across two primary radio regimes: spectral line emission from atomic hydrogen gas and continuum synchrotron radiation. The most important radio tool in extragalactic astrophysics is the 21-centimeter line of neutral atomic hydrogen, or HI line. Neutral hydrogen is the most abundant element in the universe, filling the vast spaces between stars in galactic disks. Because atomic hydrogen emits a very precise spectral line at a wavelength of 21 centimeters, due to a subtle quantum spin-flip transition in the electron-proton system, radio telescopes can map cold, invisible gas across the galaxy, regardless of whether stars are present to illuminate it. 21-centimeter radio maps of Andromeda reveal a neutral hydrogen disk that extends far beyond the bright 220,000 light-year stellar disk, reaching radial distances of over 130,000 light-years from the galactic core, giving the neutral gas disk a total physical diameter of nearly 260,000 light-years across. These radio observations allow astronomers to map the rotation curve out to extreme distances, providing the empirical proof for the massive dark matter halo surrounding the galaxy. Furthermore, high-resolution radio spectroscopy maps the velocity field of the interstellar medium, revealing complex warp kinematics, expanding shock bubbles, and narrow bridges of gas connecting Andromeda to its satellite companions. Radio line emission from molecular gas, specifically the rotational transition lines of carbon monoxide observed at millimeter wavelengths, pinpoints the ultra-dense, ultra-cold molecular clouds situated inside the dusty spiral arms, charting the precise locations where star formation will occur millions of years in the future. In addition to 21-centimeter line emission, radio telescopes observe diffuse, non-thermal synchrotron radiation generated across Andromeda's disk. Synchrotron radiation occurs when ultra-relativistic cosmic ray electrons, accelerated to near light speed by the expanding shock waves of supernova explosions, are forced to spiral around galactic magnetic field lines, Synchrotron mapping reveals that Andromeda possesses a large-scale, highly organized galactic magnetic field that threads through its spiral arms, extending over tens of thousands of light-years. This magnetic field, with a field strength of a few microgauss, plays a critical role in confining cosmic rays, regulating interstellar gas pressures, and channeling gas flows toward the central core. By assembling this multi-wavelength mosaic, combining the high-energy stellar remnants mapped in X-rays, the hot starburst rings illuminated in the ultraviolet, the warm dust ribbons traced in the infrared, and the vast neutral gas reservoirs mapped in the radio, astronomers transcend the limitations of human sight. Multi-wavelength astronomy reveals Andromeda not as a static spiral of optical starlight, but as an immense, highly integrated cosmic machine, where energy, magnetic fields, dust, gas, and stellar remnants continuously cycle through cycles of birth, death, and spatial transformation across hundreds of thousands of light years. The absolute scale and mass of the Andromeda Galaxy are not merely static measurements describing an isolated island universe. They represent the kinetic parameters of an impending, catastrophic cosmic merger that will fundamentally reshape the local group. Currently separated by a spatial distance of approximately 2.537 million light-years, the Milky Way and Andromeda are travelling toward one another along a gravitational collision course. Driven by the relentless mutual pull of their trillion solar mass dark matter halos, these two galactic titans are closing the intergalactic gap at a speed of approximately 110 km per second, or roughly 400,000 km per hour. Analysing the orbital dynamics of this approaching collision requires measuring the three-dimensional space velocity of Andromeda relative to the Milky Way. While line-of-sight radial velocity, the speed at which Andromeda moves directly toward us, has been accurately measured via Doppler spectroscopy for over a century, calculating the transverse velocity, or sideways proper motion, proved extraordinarily difficult. It required high-precision astrometric observations conducted by the Hubble Space Telescope and the Gaia Space Observatory over multi-year baselines. These precise spatial measurements confirmed that Andromeda's sideways velocity component is exceptionally small relative to its forward velocity, guaranteeing that the two galaxies are heading toward a direct, near head-on encounter rather than a glancing pass. Astrophysical computer simulations modelling the gravitational n-body mechanics of this system project that the first close physical passage between the Milky Way and Andromeda will occur in approximately 4 to 5 billion years. As the two galaxies draw near, their surrounding dark matter halos, extending hundreds of thousands of light-years into space, will be the first large-scale structures to collide and overlap completely. The drag caused by the gravitational friction between these intersecting dark matter envelopes, a process known as dynamical friction, will transfer kinetic orbital energy away from the galaxies, forcing their centers of mass to rapidly spiral inward toward one another. When the primary stellar disks execute their initial pass through one another, the optical spectacle visible from any surviving planetary systems will be breathtaking. As the outer stellar spiral arms of Andromeda and the Milky Way overlap, individual stars will almost never collide directly. The physical distance between individual stars within a galaxy is vast compared to their actual diameters. For example, if our Sun were scaled down to the size of a ping-pong ball, the nearest neighbouring star would be located roughly 1,100 kilometres away. Consequently, the direct physical impact between individual stars during a galactic merger is statistically near zero. However, while individual stars pass safely by one another like ghosts, the immense gravitational potential of both galaxies will exert tremendous tidal forces on their structural frameworks. These tidal torques will completely destroy the delicate, highly organized spiral arm architectures of both systems. As Andromeda pulls through the Milky Way, massive tidal tails composed of billions of stars, interstellar gas clouds, and dust ribbons will be flung deep into intergalactic space, creating long, glowing stellar streams that sweep across hundreds of thousands of light-years. The flat, sweeping 220,000 light-year stellar disk of Andromeda and the spiral structure of the Milky Way will be violently warped, stretched, and shredded beyond recognition. While individual stars escape direct collision, the interstellar gas clouds and cold molecular reservoirs embedded within both galaxies will undergo violent physical impacts. As the giant molecular clouds of Andromeda collide with those of the Milky Way at supersonic relative speeds, massive shockwaves will ripple through the interstellar gas phase. This supersonic compression will trigger widespread gravitational collapse within the gas clouds, initiating an intense, galaxy-wide burst of star formation known as a starburst event. During this starburst phase, the combined system will glow with extraordinary luminosity across ultraviolet and infrared wavelengths. Millions of short-lived, high-mass O and B-type stars will be born simultaneously within dense, newly formed star clusters scattered across the distorted galactic remnants. These short-lived massive stars will rapidly burn through their nuclear fuel reserves, culminating in a continuous, multi-million-year wave of catastrophic supernova explosions. These collective supernova blasts will inject immense thermal energy, heavy chemical elements, and high-energy cosmic rays into the surrounding gas, driving powerful galactic winds that will blow vast quantities of hot plasma out into the halo environment. After the initial passage, the mutual gravitational attraction of their dark matter halos will act as an elastic band, arresting the forward motion of the departing galaxies. Having converted much of their orbital kinetic energy into tidal deformation and internal thermal energy, the two damaged galaxies will reach an orbital apocenter and begin falling back toward one another for a second, even more violent encounter. This secondary passage will occur within a few 100 million years of the first, plunging the nuclei of both systems into a chaotic, rapid orbital decay phase known as violent relaxation. During this terminal stage of the merger, the supermassive black holes residing at the centers of both galaxies, Sagittarius A star from the Milky Way, weighing 4 million solar masses, and M31 star from Andromeda, weighing roughly 100 million solar masses, will plunge toward the geometric center of the combined, distorted remnant. The two supermassive black holes will form a gravitationally bound binary system, spiraling inward toward one another as they transfer orbital energy to surrounding stars through three-body dynamical friction encounters. As the binary separation between the two black holes shrinks to less than a fraction of a light-year, the emission of gravitational waves will dominate the system's energy loss. The space-time continuum surrounding the core will ripple with powerful gravitational radiation, carrying away immense amounts of energy until the two event horizons touch, merging Sagittarius A star and M31 star into a single colossal supermassive black hole exceeding 104 million solar masses. This violent black hole merger will likely trigger a brief, highly energetic, active galactic nucleus phase as surrounding gas falls inward toward the newly merged event horizon, emitting powerful relativistic jets into space. As the chaotic gravitational motions settle down over a timescale of 6 to 8 billion years from the present day, the newly merged system will complete its physical transformation. The original spiral disks, dust lanes, and distinct stellar halo boundaries of both Andromeda and the Milky Way will no longer exist. In their place will stand a single, massive, featureless triaxial system, a giant elliptical galaxy, often colloquially referred to by astrophysicists as Milkdromeda or Milkomeda. This newly formed elliptical galaxy will possess a smooth, swarm-like orbital distribution of stars. Unlike spiral galaxies, where stars orbit in an orderly, planar circle around a central axis, stars within an elliptical galaxy move along chaotic, highly eccentric orbits in 3 dimensions, resembling a glowing cloud of bees. The gas reservoirs that once fueled active star formation within the spiral arms of Andromeda will have been largely consumed during the high-density starburst phase, or driven out into intergalactic space by supernova feedback and central accretion winds. Consequently, Milkdromeda will emerge as a quiescent, red and dead elliptical system, dominated by older, low-mass population 2 stars that shine with a warm, yellowish glow. The new galaxy will span a vast spatial volume, surrounded by a massive, unified dark matter halo, weighing over 2 trillion solar masses, and an immense network of over 600 globular clusters, combining the original halo clusters of both progenitor systems alongside hundreds of newly formed massive clusters created during the merger shocks. For any intelligent observers inhabiting planetary systems far from the central core, the view of the night sky will be radically altered. The sweeping narrow band of light known as the Milky Way ribbon will be gone, replaced by a smooth, brilliant, three-dimensional stellar halo that fills the sky in every direction. The Andromeda Galaxy will no longer exist as a distant 3-degree smudge or a neighbouring spiral wheel. It will have been entirely assimilated. Its 1 trillion stars and 100 million solar mass central black hole merged seamlessly with our own galaxy to form the final, definitive structural titan of the local group. To truly grasp the scale of the Andromeda Galaxy, one must zoom out past its stars, past its dark matter halo, and even past its satellite systems, observing how it anchors itself within the large-scale architecture of the universe. Andromeda does not drift isolated in an infinite void. Instead, it serves as the primary gravitational engine of our immediate cosmic neighbourhood, connected to neighbouring systems through immense intergalactic filaments of gas and pulled along by cosmic flows that span hundreds of millions of light-years. Placing Andromeda within this broader cosmic context illustrates how local galactic dynamics are governed by the vast structural scaffolding known as the cosmic web. At the immediate scale, Andromeda is the dominant member of the local group, a gravitationally bound cluster of over 80 identified galaxies, spanning a physical diameter of roughly 10 million light-years across. Within this local assembly, the distribution of matter is overwhelmingly concentrated into 2 major subgroups, or gravitational centres, the Milky Way subgroup and the Andromeda subgroup. While the Milky Way controls a family of smaller satellite galaxies, Andromeda commands the larger and more massive gravitational domain, holding over half of the total stellar mass present within the entire local group. This dominant mass makes Andromeda the chief architect of the local group's long-term orbital trajectory. The gravitational potential well created by Andromeda's trillion solar mass dark matter halo acts as a massive anchor, drawing nearby dwarf galaxies toward it, while simultaneously pulling our own Milky Way across the intergalactic expanse. Rather than expanding away from us with the general Hubble flow of the universe, the Milky Way and Andromeda are gravitationally bound, overcoming the cosmic expansion of space to fall directly toward one another. The local group is essentially a dynamic binary system, held together by the immense mass of its 2 largest spiral titans. Extending beyond Andromeda's immediate satellite network is a direct, large-scale physical connection to the 3rd largest member of the local group, the Triangulum Galaxy, designated as Messier 33 or M33. Located roughly 850,000 light-years away from Andromeda, Triangulum is a Yun-barred spiral galaxy containing approximately 40 billion stars. For decades, astrophysicists debated whether M33 was an independent system passing by chance or a true gravitationally bound satellite of Andromeda. High-sensitivity radio observations measuring 21 cm neutral hydrogen line emission definitively resolved this question, revealing a physical connection spanning the intergalactic gap between the 2 galaxies. Deep radio maps constructed by radio telescope arrays revealed a massive, diffuse bridge of neutral hydrogen gas physically connecting the outer disk of Andromeda directly to the spiral arms of Triangulum. This feature, known as the Andromeda Triangulum Hydrogen Bridge, stretches across hundreds of thousands of light-years of intergalactic space. The existence of this gaseous bridge provides unambiguous empirical proof of a past close tidal encounter between the 2 galaxies. Dynamical computer simulations indicate that roughly 2 to 3 billion years ago, Triangulum executed a close orbital passage through Andromeda's outer halo. As Triangulum swept past Andromeda, the intense tidal gravitational forces exerted by Andromeda's mass sheared away vast quantities of neutral hydrogen gas from M33's outer disk, stretching the gas out into a long, continuous intergalactic filament. Furthermore, this gravitational encounter generated a pronounced warp in Triangulum's gas disk and triggered a wave of star formation across its spiral arms. Today, Triangulum continues its high-velocity orbit around Andromeda, bound to its primary host by this luminous gaseous thread that traces their shared gravitational history across the intergalactic void. This hydrogen bridge between Andromeda and Triangulum represents a localized node within the far larger cosmic web, the vast, intricate network of dark matter filaments and gas ribbons that stretches across the entire observable universe. On cosmological scales, matter is not distributed uniformly. Instead, gravity has pulled dark matter and gas into an interconnected web of dense nodes, long filaments, and flattened sheets, separated by vast, empty voids. Massive galaxies like Andromeda reside at the intersection points where these intergalactic filaments meet. These filaments act as cosmic pipelines, funneling pristine hydrogen and helium gas from the intergalactic medium directly into Andromeda's 2 million light-year gaseous halo. As cold gas flows along these cosmic strands, it resupplies Andromeda with the raw material needed to sustain star formation over billions of years. By mapping the velocity distribution of gas clouds surrounding Andromeda, astronomers can trace how the galaxy is continuously nourished by the surrounding cosmic web, acting as a physical junction point that channels large-scale cosmic gas into local star formation. Zooming out even further reveals that Andromeda and the entire local group are embedded within a much larger cosmic architecture, the Laniakea supercluster. Spanning over 500 million light-years in diameter and containing over 100,000 galaxies, Laniakea represents our local cosmic continent, defined by the flow lines of galaxies moving together through space. Within this supercluster, galaxies are not stationary relative to the cosmic microwave background. Instead, they are drawn along vast gravitational currents flowing toward regions of extreme mass concentration. The primary gravitational driver governing the motion of Andromeda and the local group within Laniakea is a colossal structural anomaly known as the Great Attractor. Located roughly 150 to 200 million light-years away in the direction of the Norma cluster, the Great Attractor is a massive, localized concentration of mass equivalent to tens of thousands of Milky Ways, situated near the central core of the Laniakea supercluster. The combined gravitational pull of the Great Attractor exerts a relentless force on every galaxy within its domain. As a result, Andromeda, the Milky Way, and the entire local group are travelling together through space at a staggering velocity of approximately 600 kilometers per second relative to the cosmic microwave background, streaming along a cosmic current heading toward the Great Attractor. Beyond the Great Attractor lies an even more massive gravitational anchor, the Shapley supercluster, a titanic concentration of galaxy clusters whose gravitational reach exerts an additional pulling force across hundreds of millions of light-years. Thus, the spatial reality of the Andromeda Galaxy is multi-layered and deeply interconnected. On local scales, it stands as an absolute titan, holding 1 trillion stars, commanding a swarm of satellite galaxies, and drawing the Milky Way toward a grand cosmic merger. On intermediate scales, it reaches out through intergalactic space with hydrogen bridges to bind neighbouring systems like Triangulum, and on cosmological scales, it is merely a single glowing node embedded within a filament of the cosmic web, pulled gracefully across millions of light-years along the grand gravitational currents of the universe. When we strip away the visual limitations of human sight and assemble the complete multi-wavelength portrait of the Andromeda Galaxy, we are left with a cosmic structure of profound scale and complexity. What appears through a backyard telescope as a modest 3-degree smudge of pale light is, in physical reality, one of the most magnificent architectural titans in our region of the universe. Its bright stellar disk spans over 220,000 light-years across, housing roughly 1 trillion individual stars, bound together in an intricate dance of spiraling arms, warped planes, and glowing starburst rings. At its heart sits a supermassive black hole, weighing over 100 million solar masses, commanding an eccentric disk of ancient stars that creates the optical illusion of a double nucleus. Yet, as impressive as these optical dimensions are, they represent only the innermost anchor of a far grander system. Enveloping this stellar hub is a massive halo of dark matter, weighing up to 1.5 trillion times the mass of our Sun, holding over 500 ancient globular clusters and guiding an aligned, co-rotating plane of dwarf satellite galaxies across millions of light-years. Surrounding it all is an extraordinarily vast gaseous atmosphere that reaches outward to a physical radius of up to 2 million light-years in every direction. This gaseous halo touches the outer frontiers of our own Milky Way right now, spanning across the intergalactic void and actively linking our two galaxies long before their stars ever meet. Studying Andromeda is far more than an exercise in cosmic cataloguing. Because we reside deep within the plane of the Milky Way, Our view of our home galaxy is heavily obscured by interstellar gas and dust. Andromeda acts as our ultimate cosmic mirror, a giant external laboratory that allows astrophysicists to study the structural evolution, magnetic fields, dark matter dynamics, and halo physics of a massive spiral galaxy from an exterior perspective. Everything we learn about the rotation curves, star-forming rings, and satellite interactions of Andromeda directly deepens our understanding of how galaxies grow, evolve, and die throughout the universe. Andromeda is a dynamic, living system that continues to shape the past, present, and future of the local group. It reaches across the void with gaseous bridges to touch neighbours like the Triangulum Galaxy, while falling relentlessly toward our own Milky Way to prepare for a grand merger 4 billion years in the future. If you enjoyed this scientific journey into the true physical scale of our nearest giant neighbour, please consider liking this video and subscribing to the channel for more deep cosmic explorations. We would also love to hear your thoughts in the comments below, so please let us know where in the world you are watching from today and what time it is for you right now.